In the previous theorem, in the previous class, we just studied about how to find lower Riemann sum and upper Riemann sums. These are the few questions. You just try it by yourself and then find out what is lower and what is upper Riemann sum. Today, in this class, we are going to study about theorem. So, coming to the first theorem, which says if f is mapping from closed interval a comma b to r is bounded function. Is a bounded function. They already gave that f is a bounded function and a partition P belongs to phi over a comma b. What is phi of a comma b? The entire set of partitions, as we have seen in the note point. So P belongs to phi over a comma b. Then the first condition is UPF, that is upper Riemann sum, should be greater than or equals to lower Riemann sum. This is the first condition. And the second condition is this UP comma minus F is equals to minus LP comma F. And the third condition is LP comma minus F is equals to minus U of P comma F. So this is the first theorem. Now let's look into the proof. What is the given condition? What is that they gave? Given that f is a bounded function. What is that they gave? This one. F is a bounded function. And what is P? P belongs to phi of a comma b. So what is phi? The set of all length. The set of all partitions. If you put all the partitions in one set, that is referred as phi of a comma b. So this is bounded on where it is bounded on the closed interval a comma b. Okay. Now in the next step, what is that we have to take? We have to take the partitions. And then as they gave about upper and lower Riemann sums, what should we be talking about? We should be talking about infimums and supremums, that is capital M's and small m's. So first let us take partition, that is let P is equals to A equals to x0, x1, so on up to xn is equals to B. What is this? Let this be partition. Let this be partition of closed interval a comma b, and let capital M and small m, what are they? Supremums, supremum and infimum of f on a comma b. Okay. Now as we are talking about the entire set, how many it will be? Will be having r subintervals or r lengths. So let capital MR comma small mr be infimum and supremum. Be supremum and infimum. Be supremum and infimum of f, where on the rth, when we'll be talking about the r's, when you have r subintervals. So IR is equals to XR minus 1 comma XR. What is R? 1, 2, so on up to n. Now by the definition, what is that we can talk? What is UPF? By definition of upper Riemann integral, what is UPF? Summation R is equals to 1 to n, capital MR into capital MR into delta R. What is LPF? LPF is equals to summation R equals to 1 to n, small mr into delta R. Okay. And we know that, what is that we know? And we know that capital MR is greater than or equals to small mr for R equals to 1, 2, so on up to n. Okay. Now we'll just multiply delta R on both sides. So what will that be? Capital MR into delta R is greater than or equals to small mr into delta R for R is equals to 1, 2, so on up to n. So what is, if you put summation on both sides, summation r equals to 1 to n capital mr into delta r is greater than or equals to summation r equals to 1 to n small mr into delta r. What is capital mr into delta r? It is upf, that is upper Riemann sum, which is greater than or equals to, what is summation r equals to 1 to n small mr into delta r? That is LPF. So we have proved UPF is greater than or equals to LPF. And what is that we have in the question? What is that they gave clearly? That F is bounded on closed interval a comma b. They gave it is bounded on closed interval a comma b. See now, if F is bounded, obviously minus F also will be bounded, right? If F is bounded on AB, minus F also will be bounded on closed interval AB. So what is that we can tell? We can write minus small mr is greater than or equals to capital MR. B, or take supremum and infimum, or just take small mr and capital MR. Instead of taking that point, just take minus capital M and minus small m are supremums and infimum of minus F on the interval IR. See, whenever capital M and small m are supremum and infimum for F, I can't minus M, minus capital M minus M be supremum and infimum. So that is the reason we got this step. Now, like from the first bit, we solved UPF is greater than or equals to LPF. Now moving on to the second bit. What is the second bit? The second bit is U P comma minus F. So how will you write this U P comma minus F? Just take summation R is equals to 1 to N minus MR into delta R. As we have minus MR, yeah, in the previous slide, just make sure that you take small mr as supremum and capital MR as infimum. Okay, if you consider this, we'll be able to solve the second bit. So I'm just continuing this step. Summation r equals to 1 to n minus mr into delta r. So take minus out and then write summation r equals to 1 to n small mr into delta r. What is small mr into delta r? That is LPF. So this is what we have to get, minus L into P comma F. So what is the second bit? If UP comma minus F is equals to minus L P comma F. Am I clear? Let's do the third bit. So now third bit is we have to prove LP comma minus F is equals to minus U of P comma F. So how will you solve this? What did I tell you in the before slide? You have to consider minus MR as supremum and capital MR as infimum. So putting minus as it is, like we have to consider the left hand part, that is LP minus F. So what am I doing? I'm just writing summation R equals to 1 to N minus capital MR into delta R. Again, put minus outside, you'll get summation R equals to 1 to N capital MR into delta R. So what is this? Minus UPF. Okay, for that you got to consider, Roshan, stop scribbling on the screen. Can you please just remove those lines? So like you just have to consider minus small m as supremum and minus capital MR as infimum. If you consider this, you will be able to solve the second and third bits. Okay. Now let's move into the next theorem. So the next theorem says, that is theorem 2. What is the statement? If F is mapping from A comma B to R and G is mapping from same closed interval A comma B to R, and they gave they are bounded functions. Are bounded functions, and they gave partition P belongs to phi of A comma B, same thing. So you can tell that it is set of partitions, so it has some R subintervals. Then they gave 3 conditions. The first one is U P comma F plus G up comma f plus g is less than or equals to up comma f plus up comma g. It is something like distributive property. Next, the second condition is if LP comma f plus g is greater than, if u is less than or equals to L, that is if we talk about infimum, that will be greater than or equals to LPF plus LPG. And next, the third condition is some W of P comma F plus G is less than or equals to W of P comma F plus W of P comma G. Now let's look into the proof. How are we going to solve all these three bits? So now what is that they gave? Given that F and G, given that F and G are two bounded functions. They are two bounded functions. Okay. Now what is the next step here? What are we talking about? All these three bits have f plus g. As f and g both are bounded, what will f plus g be? If f and g are both bounded functions, obviously f plus g also will be bounded. Also bounded function where on closed interval a comma b, on closed interval a comma b. Now let us talk about the partition. What is that they gave? First they gave f is bounded, g is bounded. Its addition will also be bounded. We wrote that step. Next we are talking about the partition. So let p is equals to a is equals to, what is the how are we going to define the partition? A equals to x naught, x1, so on up to xn is equals to b. So what is this? B partition, be the partition on closed interval a comma b. We spoke about functions which are bounded. We spoke about its addition. We spoke about partition. The next step comes to supremums and infimums. Why are we defining supremum and infimum? Because in the question, they are asking us to find use, that is upper Riemanns and lower Riemanns. So for that, just to write the prove that one, we are making use of MR and small mr. So what are they? Supremums and infimums. Infimum where of f plus g. We are now talking about the two functions, that is those additions f plus g on the rth subinterval. What is IR? IR is equals to xr minus 1 comma xr, where r is equals to 1 to so on up to n. Okay, we spoke about m, capital MR and small mr. Now we will talk about its derivatives. Okay, now talking about its derivatives, let capital MR, someone please unmute yourself, sorry, mute yourself. Capital MR dash comma small mr dash, the supremum and infimum of f on IR. Okay, so as MR and MR are supremum and infimum, its derivative will also be supremum and infimum, and double derivative will also be supremum and infimum of IR. Okay, on f, like this is on f and this is on g on IR. Okay, as we have m's, capital M's as supremum and small m's as infimum. Next we have to talk about like these both functions for both f and g. So what will that be? What will supremum be? M r dash and MR double dash are both what they are talking about the capital M's. So what are they? Those both are supremums of capital F and supremums of f and g of the function f and g on IR. Now we are talking about Mohan. Please mute yourself. MR dash and capital MR double dash are both supremums of f and g on IR. Now, what is that we'll talk about? We'll talk about the functions of f and g. So, what is that? F of x is less than or equals to capital MR dash. Okay. And g of x is less than or equals to capital M R dash. If you have to know why am I writing less than or equals to, you have to know the definitions of supremum and infimum. If you do not know, please go through the definitions of that and learn. For all x belongs to IR, because I've already explained them. And the next step is f of x, like addition of these both. F of x plus g of x is less than or equals to capital MR dash plus capital MR double dash for all x belongs to IR. Now, these f of x and g of x we can write as f plus g of x, which is strictly less than or equals to MR dash plus MR double dash for all x belongs to the rth interval. So what is that we can conclude? MR dash plus MR double dash is upper bound. It is the upper bound of what? Of these f plus g. So MR dash and MR double dash is upper bound of f plus g on interval IR. But MR is least upper bound of f plus g. Okay, like these both are normal upper bounds, but what is the least upper bound? That is supremum. Capital MR is the least upper bound. I'll just write LBU, least upper bound of what? Of f plus g on IR. Okay, am I clear till here? Now what will be the next step for this? As this is the least upper bound, how is that we can write? We can conclude this as capital MR is less than or equals to MR dash plus MR double dash. Okay, just remember this one. As it is the least upper bound, we can write this as MR is less than or equals to MR dash plus MR double dash. Now moving on to the first bit of the theorem. What is the first bit? Says U P comma F plus G. How should we prove this? U P comma F plus U P comma G. So what is the formula for this summation? R equals to 1 to N MR into delta R. So what is MR? It is less than or equals to summation R equals to 1 to N. This can be written as MR dash plus MR double dash into delta R. Okay, and this is less than equals to, like, multiply this with this, and then we'll have summation R equals to 1 to N MR dash into delta R plus summation R equals to 1 to N MR double dash into delta R. Okay, so what is this? This is U P comma F plus this is U P comma G. We have earlier defined that for one derivative, that is supremum for that is the upper bound of f, and if you have m r double dash, that is if you have two derivatives, that is the upper bound for g. Okay, hence we prove this U P comma F plus G is less than or equals to U P comma F plus U P comma G. Okay, now let's look into the second step. What is the second step? I mean, what is the second condition that they gave? Before moving on to the second one, we have to just prove one bit. That is, now we have to consider small mr dash and small mr double dash. Okay, let this be infimums. Till now we spoke about supremum. Now we are talking about infimum. Let this dash and double dash be the infimum of what? Of the functions f and g on the IR, that is the rth subinterval. So what is that? As we are talking about the infimum, this f of x will be greater than or equals to mr dash, and g of x will be greater than or equals to mr double dash, where for all x belongs to IR, the rth subinterval. Now add these both. So f of x plus g of x is strictly greater than or equals to mr dash plus capital MR double dash for all x belongs to IR. So how will you write this? You can write it as f plus g of x, which is greater than or equals to MR dash plus MR, this is small mr, MR double dash for all x belongs to IR. So this is what we had. But what is this MR plus MR double dash? They are the lower bounds. So MR dash plus MR double dash is lower bound. It is the lower bound of what? Of F plus G on IR. But what is the greatest lower bound? That is the infimum. MR is the greatest lower bound. It is the greatest lower bound of what? Of F plus G on the interval IR. So how will you write this? You can write this as small mr is greater than or equals to mr dash plus mr double dash. So this is the one which you have to remember. Small mr dash is small mr is greater than or equals to mr dash plus mr double dash. Now we will be talking about the second bit. What does the second bit say? L P comma F plus G. So how does this define? Summation R equals to 1 to N small mr into delta R. So this is greater than or equals to summation R equals to 1 to N. What is small mr? Which is greater than mr dash plus mr double dash into delta R. Same thing, just multiply summation R equals to 1 to N mr dash into delta R plus summation R equals to 1 to N mr double dash into delta R. So what is this one? It is LPF and this is LPG. So what is that we have proved? LPF plus G is greater than or equals to LPF plus LPG. Okay, am I clear till here? Now we'll just look into the third bit. What is the third bit? The third bit is given as W, WP comma F plus G. So what does this say? W is like U minus V. So sorry, U minus L. What is W actually? Oscillatory sum. Oscillatory sum. It is either defined as O of something or W of something. When I explained you the definition, I just gave that it is defined like this, either O or either W. So what is the definition of that? U minus L. So U of P comma F plus G minus L P of F plus G. So this is less than or equals to U P comma F plus U P comma G from the first bit. Again minus LP comma F plus LP comma G. So removing the brackets, you'll get LP comma F plus UP comma F plus UP comma G minus LP comma F minus LP comma G. Now you can write this as UP comma F minus LP comma F plus UP comma G minus LP comma G. What is U minus L? Oscillatory sum. So W of P comma F plus W of P comma G. Hence proved. After this, there is a note point. I'll just explain you that. So what does a note point say is, note, if f is a function mapping from a comma b to r, there is a function which is mapping from a comma b to r. Obviously, it should be a bounded function, which is a bounded function. And there are two partitions. We are just taking P1, P2. There are two partitions which belongs to phi of a comma b, such that P1 is less than P2, then UPF, that is UP1 comma F, is greater than or equals to UP2 comma F. This is the first bit. And the second says, if LP1 comma F is less than or equals to LP2 comma F. And the third one is W, that is oscillatory sum. W of P comma F is greater than or equals to W of P2 comma F. So this is a note point. And in the next theorem will continue in the next class.